Hello, I'm Adam Taylor. I'm going to talk to you about my Hackster project today, which is based around creating a health and usage monitoring system with a FPGA and using a RISC-V microprocessor inside it. What we're actually going to create is this here, which is the Digilent Spartan S7 board. There are two PMODs on these. These allow us to monitor the environment that we're in. And we have, of course, we have the FPGA in the middle. And throughout this application, what we're going to talk about and we're going to create is we're going to create the actual application that sits in the FPGA. We're going to create a RISC-V microprocessor that's running in that. And then we're going to write some software that runs on the RISC-V. And we're going to write some Python that runs on our PC to see and log the data that's coming out of it. The reason why we created this project actually is quite interesting. And that's because for a lot of applications, we want to be able to monitor things such as acceleration in all three directions, temperature, humidity. And that's really important for a lot of applications because if you can understand the dynamic forces and environmental forces that equipment's been subjected to, you can work out how its lifetime is going to be, how its reliability is going to be, and generally you can get a much better picture of its failure rate or its acceptability for the application in hand. So we find these health and usage systems in a range of applications, from aircraft to vehicles to even space systems as well. So let's take a look. Let's dive in and spend a couple of minutes and take a look at the design. We're gonna split this across a couple of applications. We're gonna take a look at the project in Vivado, which is where we've created the application, and we've created the hardware element that goes into the FPGA. Then we'll take a look at Vitis, where we've written the software that's in there, and then we'll quickly wrap up with a little bit of a look at the overall application running and using the Python to grab that data. So as I said, when we wanted to start out creating this application, we need to create an FPGA design. And that is the design that is programmed into the FPGA. Until we do that, it's just a configuration of an array of configurable logic blocks, block RAMs, memories, DSP elements, and we need to harness that and focus that into something functional. So because we're working with an AMD Spartan 7 FPGA, we need to use the AMD Vivado Design Suite to do this. And one of the nice things about the Vivado Design Suite is that we can use the IP integrator to actually create our design. So this design you can see here, this graphical design over on taking up the majority of the display, is actually the FPGA design. So I've not written any VHDL or Verilog to create this one. All we've done is pull together existing elements from the Vivado IP library. So obviously the main thing in the middle here that we can see is we have a RISC-V microprocessor. This is the Microblaze 5, the AMD new processor. And being a soft-core processor, so that's a processor that's implemented in the logic cells and logic resources that are available in the FPGA, this is actually really configurable. So we can see that we can change the configuration of the processor. We can change its optimization, whether we want this to be designed for fitting in a small FPGA or designed for performance, and that will make a difference as to how much logic and how many processing stages are included. As we go through this, we can take a look at the actual optimizations that we want to apply to the RISC-V processor. Do we want to enable code compression, for example? Now, because I want my example to run from the block RAM memory that's available in the FPGA, and this is a relatively small FPGA, then yes, I've enabled code compression on this. But I've not used too many of the other options in this because actually this is a relatively simple application that we're going to be doing. I've enabled the AXI, which is the exceptions for the AXI, and I'm also going to enable the AXI interfaces that allow us to talk and communicate with the external world. So if you're not familiar with what AXI is, it stands for the ARM Extensible Interface, and it is a memory mapped read and write channel to transfer data efficiently within the FPGA. So we're going to do this, and that's going to allow our processor to be able to connect to our peripherals in the FPGA itself, in the fabric logic itself. So within the logic itself, within the fabric, we've put in a PMOD, an IP core for a PMOD navigator. So this gives us the XYZ parameters. we've put in the PMOD Hygro, so this gives us the temperature and the humidity. Because I want to communicate with the external world, we've also had to define a UART, so a simple serial UART interface. And then we have some simple GPIO just to test with some LEDs and allow some correction of that. Wrapping up the rest of the system, we have an AXI crossbar to allow the interconnect from the processor to the peripherals. We have the local memory, so this is where our program is going to execute from. And then we have the basics that we need to be able to connect over JTAG and download and debug our application. And the remainder of the logic around here, the clock wizard, the processor reset block, is designed to generate the clocks that are needed for our application. In this case, we're just working from a 100 megahertz clock. And we've also connected in, although I don't use them actually in the application, I connected in the AXI interrupt controller such that we can have an interrupt driven system. Once we've got this, what we need to do is we need to compile this so it goes through synthesis, place and route, and generate a bit stream, which we can see. Once we have that bit stream, as we can see here, the bit stream is written completely, and we can see then the utilization of the FPGA. So we can see how much of the logic resources of the FPGA this design is taking, and it takes about 12% overall of the logic, which is not too bad. Having this now, we're then able to take through and recreate or even start rewriting our software to run on that embedded RISC processor. So let's take a look. At that. To do this, we use a program called Vitis. And Vitis has a simple concept. It takes the bit stream that we've created in Vivado, along with some additional information such as the sensors, the software drivers that are used, the configuration of the microblaze, and the address space as well of the peripherals. And then that allows us to create two things within Vitis. The first thing is it allows us to create is our application. But to run the application, we really need a board support package, or what is in Vitis is called a platform. So we get a platform from the bitstream. So we can take our bitstream, we can pull it into Vitis, and that will create a configuration platform for us that has everything we need in the design. So we can see under the microblaze, we can see the standalone because we're working with a standalone microblaze. We can see all of the things that we need, such as the board support package, to be able to work with this. So here's where we can change the drivers, the peripherals, and anything like that. And this should all reflect through from our hardware design that we've just seen in Vivado. Once we've got that, obviously the next thing to do is to write our application software. So we've written our application software and we've tried to make it scalable. So I've created a simple project. And in this simple project, the first thing we do is we initialize the PMODs. We say that we're going to start command parsing, and then we call this function here called CLI command parser. Now this, you'll see this CLI actually in the codes available in the project. This is something that we've been using more and more in our projects because it's a command line interpreter. So that allows us to receive data over from the UART. Over the serial port using the UART, and then we parse that to do it. So we have simple commands such as read the accelerometer in the X, the Y, the Z, and then we will process that data and send that data back. We also have simple read and write commands which will allow you to read and write any location in the memory stream. So by doing this, what this means is that our software application that sits and runs on our host PC that's running under Python can then access and control the software any way that we want and read and write with the sensors. So if we open up our application in our Python application, what we'll see is we have a standard Python application that connects over the serial port. We have a function that sends down the command to the user, so the command that we want, whether it be read the accelerometer. And once we've done that, we get the data back, and I want to plot the data on a graph, as you'll see in a minute. So that's what we do there. In the main function, obviously, we basically set up the configuration, initialize the serial port, set up our graph, and then we connect to that serial port and run through. What we see at the end of this is we see a plot, as you can see here, with the real-time data coming up of it from the board. And as we pick the board up and move the board about, what we should see, hopefully, as this updates, is you can see the data is being updated. The real-time plot is being updated, and we can see the changes that are going to it. So we could be logging this and seeing where it goes. So this really is a quick introduction to our project. I hope you've liked it. It's relatively simple to do. You don't need to be an FPGA expert to do this. The instructions are fully in our Hackster project. All you've got to do is just walk through the instructions and follow through the instructions, and yeah, enjoy and have fun.